SALMON is open source software that performs first principles calculations on the interaction between light and matter. In this video, we use the acetylene molecule as an example to explain the calculation for a scenario wherein a strong pulsed electric field is applied to a finite-sized substance such as a molecule or nanostructure. This exercise is explained according to the manual on the SALMON website. You can access the SALMON website using this URL https://salmon-tddft.jp. For this exercise, we assume that the ground state calculation for the acetylene molecule has been completed using SALMON. If you have not done so, perform the ground state calculations for the acetylene molecule. Please refer to Introduction to SALMON, Execution, Exercise 1, Ground State of Acetylene Molecule on the Documents page of the SALMON website for ground state calculation of the acetylene molecule using SALMON. Let us begin the exercise. Click the Use SALMON button on the left sidebar on the SALMON website to display the SALMON manual. Click the Exercises button on the left sidebar of the SALMON manual. On the left sidebar of the SALMON manual, click the C2H2 Isolated Molecules button that is below the Exercises button. Here we perform the calculation for Exercise 3, Electron Dynamics in C2H2 molecule under a pulsed electric field. The function obtained by differentiating the vector potential of this formula over time is used as the electric field applied to the molecule. It is a function with a central frequency of omega and a cosine square envelope. The parameters that characterize this electric field, such as amplitude E_0, frequency omega, plus length t, and the z direction, the direction of the electric field, are specified in the input file. Using this electric field and the ground state as the initial condition, we solve the time-dependent Kohn-Sham equation. The electric field is incorporated as a scalar potential of the form V equals EETZ. Now let us use SALMON to calculate the electronic motions that occur when this electric field is applied to the acetylene molecule. It is assumed that the ground state calculation of the acetylene molecule has been completed in Exercise 1. The files required for this calculation are contained in the salmon/samples/exercise_03_C2H2_RT/directory. Let us copy the files to exe3, the directory where the calculation would be performed. C2H2_RT_pulse.inp is an input file. C_RPS.dat and H_RPS.dat are files of pseudopotentials of the carbon atom and hydrogen atom respectively. These were used earlier in the ground state calculations. In addition, we require the results obtained from the ground state calculation. Suppose you perform ground state calculations in a directory called exc1. When these calculations are completed, a directory called data_for_restart is created in that directory. It would contain data such as the orbital function of the ground state. Copy the directory as a whole to the exc3 directory, and alter the directory name from data_for_restart to restart. Let us examine the content of the input file c2h2_rt_pulse.inp. Most of the content is identical to that of the input file used to calculate the ground state. Here, we consider only the differences. In the first namelist calculation, the value of the keyword theory is tddft_pulse. This was DFT in the ground state calculations. The name lists system, pseudo, functional, and rgrid must have settings identical to those in the ground state calculations. The name list tgrid specifies content related to time increments. dt specifies the time interval for calculating the time evolution of the wave function. Here, the time interval is 1.25 times 10 to minus 3 fs. The unit here is femtosecond, fs, which is equal to 1.25 as, attoseconds. Nt is the number of time steps of the time evolution calculation, which is 5,000 times here. That is, the time evolution calculation is performed for 6.25 fs. EM field is a name list that specifies the electromagnetic field to be applied to the system. By equating AE_shape1 to ACOS2, the electric field is provided using the vector potential. Furthermore, it is specified that the envelope is cosine square. I_WCM2_1 equals 5.00 D13 specifies that the strength of the applied electromagnetic field is 5 times 10 to 13 watt per square centimeter. TW1 equals 6.00 D0 specifies that the length of time from the beginning to the end of the pulse is 6 femtosecond. Omega 1 equals 3.10 D0 specifies that the average frequency of the pulse is 3.1 eV. The frequency is multiplied by Planck's constant, and the product is expressed in units of energy. EPDIR_RE1 1 to 3 specifies the direction of the electric field. In this case, because the x and y directions are 0 and z direction is 1, the electric field is in the z direction. The name list analysis specifies the information required to convert the dipole moment expressed as a function of time into a function of frequency using Fourier transform. dE is the energy interval, which is 0.01 eV here. N energy is the number of energy points for which Fourier transformation is performed. Here, calculations are performed for 10,000 points in increments of 0.01 eV. Thus, calculations are performed from 0 eV to 100 eV. Atomic_COOR is a name list that specifies the coordinates of atoms. However, this is also shared with the ground state calculations. Refer List of input keywords on the website for the name lists and keywords available in your input files. All the keywords are explained there. Let us perform the calculation. In the system used here, the command for MPI calculation is MPI-exec. Here, calculations are performed with the MPI process count as 2. When the calculation is completed, several output files would be generated. A sample output file can be downloaded from the SALMON website. Let us observe the contents of a few of these files. First, let us consider the standard output file c2h2_rt_pulse.log. The first part of the file shows the version number of SALMON used in the calculation. Then, the input variables used in the calculation are displayed. When the preparations for performing the calculation are complete, the time evolution calculation begins. The number of time evolution calculation is displayed in time step, and the time is displayed in time. The unit is femtosecond. The x, y, and z components of the dipole moment are written in units of angstrom. The following quantities are shown further to the right. Electrons is the number of electrons calculated from the norm of the orbital function. The calculation algorithm does not stringently preserve the norm, hence it starts at 10 and decreases marginally. Total energy is the total energy of the electronic system. Finally, ITERVH is the number of convergences of the conjugate gradient method performed each time to solve Poisson's equation. Let us discuss regarding the other output files. In c2h2_rt.data, the quantity obtained by the time evolution calculation is expressed as a function of time. Similar to other files, the quantity that the file contains is described at the beginning of the file. Here we illustrate the figure that was drawn using the time in femtoseconds in the first column and the z component of the electric field in the 7th column. This figure was drawn using the z component of the dipole moment in the 19th column. If the electric field is weak, the electric field and dipole moment are proportional, with polarizability as the proportionality constant. However, because the calculation here uses a significantly strong electric field, a strong nonlinear response is highly evident, and the proportional relationship collapses over time. Next, let us consider c2h2_pulse.data. This file contains information regarding the time and frequency after the Fourier transformation. This figure illustrates a plot of the quantity in the 10th column against the energy in the logarithmic scale. The vertical axis, the 10th column, is the square of the magnitude of the dipole moment in the z direction after the Fourier transformation. Many peaks appear at odd multiples of the fundamental frequency of 3.1 eV. This is called high harmonic generation. C2H2_RT_energy.data contains the energy of the system as a function of time. In this figure, the horizontal axis represents time and the vertical axis represents the excitation energy of the molecule based on its ground state. You can observe the excitation of the molecule when an electric field is applied to it. The frequency of the electric field is 3.1 eV, which is smaller than the HOMO-LUMO energy gap of the molecule, and no linear optical excitation occurs. However, electronics excitation occurs through a nonlinear process because the electric field is highly strong. Let us perform our calculation with different parameters in the input file. In the namelist EM field, where you enter the parameters of the electromagnetic field, the strength of the electromagnetic field I is weakened from 5 times 10 to 13 watt per square centimeter to 1 times 10 to 12 watt per square centimeter. Then the frequency is altered from 3.1 eV to 9.28 eV. This frequency is the energy of the state in which the acetylene molecule strongly absorbs light in the linear response calculation performed for exercise 2. The electric field diagram reveals that the period is shortened because of the increase in frequency. The dipole moment diagram reveals that the dipole moment does not decrease even when the electric field decreases gradually. This is explained by the fact that the energy is transferred resonantly because an electric field with a frequency matching the energy of the excited state of the molecule is applied. We can observe that the excitation energy increases monotonically over time. Compared with the previous calculation, the strength of the electric field is 50 times smaller, whereas the value of the excitation energy is higher. This is also because the larger excitation occurred because of the application of an electric field with a frequency that matches the energy of the excited state. This concludes the explanation for exercise 3.